What if I told you the fabric of reality isn't as flawless as it seems? Beneath the serene expanse of the cosmos, hidden fractures could lurk, cosmic strings, relics of the universe's fiery birth, thinner than an atom yet dense enough to bend spacetime itself. These bizarre threads, predicted by theory but never seen, might be the universe's most enigmatic architects, weaving chaos into the very laws of physics. Picture a crack in a frozen lake, but instead of water beneath, it's the fabric of existence splitting open, warping time, twisting light, and rewriting the rules we thought were set in stone. Scientists have spent decades simulating these cosmic strings, and what they've uncovered is stranger than fiction. Imagine stepping into a time loop where the past and future blur into an inescapable knot, or hearing gravitational echoes ripple across the cosmos like whispers from another dimension. These simulations reveal universes where black holes dance in perfect sync, where entire galaxies flicker like mirages, and where the speed of light isn't just a limit, it's a suggestion. Each discovery peels back another layer of spacetime's secrets, forcing us to question whether we've ever truly understood reality at all. This journey isn't just about abstract physics, it's about the universe's hidden blueprint. If cosmic strings exist, they could hold clues to the Big Bang's aftermath, to dark matter's elusive nature, even to the ultimate fate of everything. And as we explore these 26 mind-bending outcomes, from spacetime's phantom vibrations to the eerie possibility of parallel universes brushing against our own, you'll begin to see the cosmos not as a static stage, but as a living, twisting, unpredictable entity. So buckle up, we're about to venture into the cracks of reality, where the ordinary becomes impossible, and the impossible might just be real. First, let's tackle one of the most startling revelations from these cosmic string simulations: black holes appearing out of nowhere, defying everything we thought we knew about how they form. Normally, black holes are born from the dramatic collapse of massive stars, their cores imploding under gravity's relentless pull. But cosmic strings rewrite the script. These ultra-thin, unimaginably dense filaments carry so much tension that they can snap spacetime itself, twisting it into a knot so tight that a black hole just pops into existence. No star death, no supernova, just pure geometric chaos birthing a singularity. Think of it like a rubber band stretched to its limit. At some point, the strain becomes too much and it snaps. Now replace that rubber band with a cosmic string, a thread of energy left over from the universe's infancy, and the snap isn't just a break, it's a tear in reality so severe that it crumples into a black hole. What's even wilder, these black holes wouldn't behave like the ones we're familiar with. Without the debris of a star, they'd be near invisible, drifting through space like ghosts, detectable only by their gravitational whispers. This idea flips astrophysics on its head. If cosmic strings can spawn black holes so effortlessly, it could explain the existence of primordial black holes, theoretical objects thought to have formed in the universe's first chaotic moments. These ancient, elusive black holes might be hiding in plain sight, woven into the fabric of the cosmos itself. And if they're out there, they could hold answers to some of our biggest mysteries, from dark matter's grip on galaxies to the faint, unexplained gravitational ripples we've detected across the cosmos. But here's the real kicker. If these string-born black holes exist, they could challenge our understanding of physics itself. Einstein's equations predicted black holes, but even he might have been stunned to learn they could form from something as bizarre as a space-time crack. It's a reminder that the universe is far stranger, far more inventive than we've ever dared to imagine. And this is just the first ripple in the cosmic pond. Wait until you see what else these strings can do. Now imagine a thread so powerful, it doesn't just bend space, it twists time into a knot. Cosmic strings don't just warp the universe's fabric, they might stitch it into loops where the past and future collide. In simulations, these bizarre filaments create something called closed time-like curves, paths where time folds back on itself like a Möbius strip. A particle drifting too close could find itself caught in a temporal whirlpool, reliving the same moment over and over, or worse, crossing its own timeline in ways that defy logic. Think of it like walking on a treadmill that's also a time machine. Normally, time marches forward, an arrow flying straight from past to future, but near a cosmic string, that arrow could curve into a circle. You might travel for years only to return to the exact instant you left, watching your past self begin the same journey. The strangest part, this doesn't necessarily break physics. Einstein's equations allow for these loops. They're mathematically possible, even if they turn our intuition upside down. Yet the implications are dizzying. If time loops exist, could you send a message to your past self? Would you remember receiving it? Simulations suggest particles might briefly escape causality's grip, creating paradoxes that make scientists shudder. Picture a single photon entangled in its own history, influencing events before it even exists. It's like dropping a pebble into a pond, only to watch the ripples flow backward in time. Some theories propose these loops self-correct, weaving new timelines to avoid contradictions, almost as if the universe has a failsafe against chaos. But here's the real question: could cosmic strings be nature's time machines? If so, they'd be wildly unpredictable. Unlike the tidy portals of sci-fi, these would be turbulent, one-way trips with no guarantee you'd return intact. Gravitational forces near a string could shred matter into quantum confetti long before time bends. And even if you survived, you might emerge into a past where the slightest change cascades into cosmic catastrophe. Perhaps that's why we've never found one. Time loops might be too unstable to last, vanishing as quickly as they form. Or maybe they're hidden in plain sight, disguised as gravitational anomalies or dark matter's fingerprints. Either way, these simulations force us to confront a humbling truth. Time might not be the steady river we thought. It could be an ocean with whirlpools, eddies, and currents we're only beginning to map. And somewhere in those depths, cosmic strings might be weaving the most impossible threads of all. Next, consider this. What if these strings don't just twist time? They rewrite the laws of physics entirely. The third outcome is even stranger. Gravitational waves usually arrive like cosmic symphonies, steady, predictable ripples from colliding black holes or neutron stars. But cosmic strings, they'd shred the rulebook entirely. Instead of smooth undulations, these spacetime defects could send out violent, staccato bursts of gravity-sharp, jarring signals that would light up detectors like fireworks in the dark. Picture the difference between a rolling ocean wave and a sudden crack of thunder. That's how radically these bursts would stand out from anything we've ever observed. What makes these gravitational wave bursts so bizarre is their origin. When cosmic strings vibrate or snap, a phenomenon called a kink or cusp, they don't just warp spacetime gently. They whip it like a cracked towel, sending out concentrated shockwaves of gravity. Simulations show these bursts would pack enormous energy into fleeting moments, sometimes lasting just milliseconds. Yet in that blink of an eye, they'd carry more telltale clues than years of steady signals. The waveform would spike abruptly with a distinct mathematical signature, like a fingerprint pressed into the fabric of reality itself. This could revolutionize how we hunt for cosmic strings. Current observatories like LIGO and Virgo are tuned for mergers, not bursts. but next-generation detectors like the planned space-based LISA mission might finally catch these elusive cracks in spacetime. The key lies in their unpredictability. Unlike black hole collisions which build up over orbits, string bursts would appear without warning, vanishing just as fast. It's like trying to photograph lightning in a pitch-black sky. You'd need a camera fast enough and sensitive enough to catch the split-second flash, and if we did detect them, the implications would shake astrophysics to its core. These bursts wouldn't just prove cosmic strings exist, they'd reveal details about their size, tension, and even how they interact with dark matter. Some theories suggest strings could be tangled into vast networks, humming with gravitational static. Others propose they might decay over eons, leaving behind these explosive echoes. Either way, each burst would be a time capsule from the universe's first moments, carrying secrets about how spacetime itself knitted together after the Big Bang. But here's the haunting part. We might have already missed them. Without the right tools, these signals could slip through our nets, mistaken for glitches or cosmic noise. It's a reminder that the universe often hides its greatest wonders not in plain sight, but in the spaces between what we think we know. And as detectors grow more advanced, we might finally tune our ears to the whispers and cracks of spacetime's hidden architecture. Fourth bizarre outcome takes the strangeness of cosmic strings and scales it up to cosmic proportions. Instead of solitary threads drifting through the void, simulations reveal these spacetime defects would tangle into vast, sprawling networks. Think of a web woven not from silk, but from the raw fabric of reality itself. These intricate labyrinths could stretch across billions of light years, their gravitational fingerprints subtly guiding the universe's grand design. Here's where it gets eerie. The universe's largest structures, colossal galaxy clusters and superclusters, aren't scattered randomly. They align along invisible filaments like beads on a string. For decades, scientists assumed dark matter alone sculpted these patterns, but cosmic string networks offer a radical alternative. These primordial flaws in spacetime might have acted as scaffolding, their gravitational pull funneling matter into dense ribbons where galaxies eventually blossomed. Picture an invisible highway system with cosmic strings as the intergalactic freeways directing traffic over billions of years. The simulations paint an even wilder picture. As the universe expanded, these networks wouldn't stay static. They'd evolve, vibrating like plucked guitar strings. Some strands might snap, releasing bursts of energy we now hunt as gravitational waves. Others could reconnect, tying spacetime into knots that warp the paths of light itself. If you looked at the night sky through gravitational lenses, you might glimpse faint, ghostly imprints of this web, stretches where background galaxies appear distorted, as if viewed through shattered glass. But the real shocker, these networks could still be here today. Unlike most relics of the Big Bang, cosmic strings wouldn't decay easily. They might lurk between galaxies, too thin to see but massive enough to tug stars subtly off course. Some theories even suggest dark matter, the universe's most elusive substance, could cluster around these filaments like frost on a windowpane. If true, it would mean we've been staring at cosmic strings' shadows all along, mistaking their influence for something entirely different. This isn't just about rewriting cosmology textbooks. If string networks exist, they'd be a time capsule from the universe's first trillionth of a second, preserving clues about how spacetime itself crystallized from the chaos of creation. Future telescopes mapping the cosmic web in unprecedented detail might finally spot their signature, a telltale kink in the distribution of galaxies, or a gravitational lensing pattern too precise for dark matter alone to explain. Until then, these simulations remind us, the universe's blueprint might be written not in stars or particles, but in the tangled threads of spacetime's earliest scars. And if you think that's mind-bending, wait until you hear the fifth outcome, where cosmic strings don't just shape space, but become portals to realms beyond our own. Fifth bizarre outcome might rewrite everything we thought we knew about dark energy. Imagine a crack in the foundation of reality, not just warping space, but bleeding phantom energy into our universe like steam from a pressurized pipe. That's what some simulations reveal about cosmic strings. They could be channels for dark energy, the mysterious force accelerating the cosmos's expansion. And if that's true, these space-time defects aren't just relics of the Big Bang. They're active players shaping the universe's fate. For decades, dark energy has been the ultimate enigma. We know it's there because galaxies are flying apart faster than gravity should allow, but its strength seems oddly inconsistent, stronger in some voids, weaker near massive clusters. Cosmic strings could explain this patchwork effect. Their immense tension might destabilize the quantum vacuum around them, creating localized surges of dark energy where strings intersect or vibrate. Picture a sponge soaking up water unevenly, some areas drenched, others barely damp. That's how these leaks could warp the fabric of expansion itself. The math behind this is staggering. Quantum theory suggests empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. Normally, their effects cancel out, but near a cosmic string, simulations show spacetime's extreme curvature could amplify these fluctuations, funneling vacuum energy into our universe like a cosmic siphon. Some models even suggest strings might act as dark energy capacitors, storing and releasing it in bursts that could momentarily accelerate expansion in unpredictable pockets of the cosmos. This would solve one of astrophysics' biggest headaches: why dark energy's density appears so finely tuned. If strings are regulating its flow, the balance isn't coincidental, it's dynamic, shaped by the interplay of spacetime's primordial flaws. Telescopes mapping the universe's expansion in unprecedented detail might soon spot telltale patterns, regions where acceleration spikes or dips align with invisible string networks. Yet the implications go deeper. If cosmic strings really are dark energy's conduits, they could bridge quantum mechanics and cosmology, two fields that famously resist unification. Strings might be the missing link between the infinitesimal and the infinite, proving that the universe's largest mysteries are written in the smallest stitches of spacetime's fabric. And if we're right, these threads don't just connect points in space, they might be weaving the very future of reality itself. But the strangest twist: this energy leakage could be temporary. Some simulations hint that as strings decay or reconnect, their dark energy faucets might shut off entirely. If so, the universe's acceleration isn't guaranteed. It could slow, stop, or even reverse as these spacetime seams heal. That would mean our cosmic fate isn't sealed by some immutable constant, but by the restless dance of defects left over from creation. And that's a realization profound enough to make even the most seasoned cosmologists pause. Quantum entanglement is already strange enough when it happens in a lab, particles linked across a room, instantly mirroring each other no matter how far apart. But cosmic strings could take this phenomenon and stretch it across the universe. Picture two particles, each sitting on opposite sides of a galaxy, bound together by an invisible thread of spacetime itself. This isn't just entanglement, it's entanglement on a scale so vast it rewrites the rules of what we thought was possible. The secret lies in how cosmic strings warp reality. These defects aren't just static cracks, they're dynamic, vibrating structures that could weave quantum connections into the fabric of space. Simulations suggest that as particles pass near a cosmic string, their properties might become intertwined, not just with each other, but with the string's own quantum state. The result, a network of entangled particles spanning light years, even megaparsecs, linked in ways that defy classical physics. What's truly mind-bending is the potential for communication. In theory, changing the state of one entangled particle instantly affects its partner, no matter the distance. If cosmic strings have woven these connections across the cosmos, it raises a tantalizing question. Could civilizations, if they exist, use these quantum links to send messages faster than light? Imagine a galaxy-wide internet, not bound by the speed of light's limits, but powered by the universe's own hidden wiring. Of course, the challenges are immense. Maintaining coherence over such distances would require conditions so precise they border on fantasy. Even a single stray photon or gravitational wave could decohere the system, collapsing the entanglement into noise. And yet, the mere possibility forces us to reconsider quantum mechanics boundaries. If entanglement can scale up like this, does it mean the universe is fundamentally more interconnected than we ever imagined? Some theories go even further. If cosmic strings were abundant in the early universe, they might have imprinted their entanglement onto the cosmic microwave background, the afterglow of the Big Bang. This could mean the entire universe is subtly linked by a web of quantum correlations, a hidden architecture of unity beneath the chaos. Future telescopes hunting for anomalies in the CMB might one day spot the fingerprints of these primordial connections. But here's the kicker. If entanglement really does stretch across galaxies, it could solve one of physics' biggest puzzles: how to reconcile quantum mechanics with gravity. These cosmic scale links might hint at a deeper theory, one where space-time and quantum fields aren't separate, but woven together by threads we're only beginning to glimpse. And if that's true, then cosmic strings aren't just flaws in reality. They might be its most essential stitches. Seventh bizarre outcome bends the mind even further. What if space-time itself could freeze solid? Not metaphorically, but literally crystallizing into rigid, lattice-like structures under the influence of cosmic strings. Picture the universe's fabric not as a smooth, flowing sheet, but as a patchwork of frozen segments where the rules of physics fracture into something unrecognizable. These cosmic ice patches wouldn't just warp reality, they'd rewrite it, creating pockets where matter behaves in ways that defy every textbook. The key lies in how cosmic strings distort the quantum vacuum. Normally, spacetime is a seething ocean of virtual particles, constantly flickering in and out of existence. But simulations show that when strings interact with this quantum foam under extreme conditions, like near the cores of galaxies or in the early universe's crushing densities, they could lock spacetime into fixed crystalline patterns. Think of it like supercooled water suddenly freezing around a speck of dust. The string acts as that seed, forcing the chaotic quantum fields around it to align into orderly, repeating structures. Within these crystallized zones, the consequences would be staggering. Light might travel at different speeds depending on its direction, like light bending through a prism, except the prism is spacetime itself. Particles could gain mass unpredictably, or even tunnel through barriers that should be impenetrable. Gravity might become anisotropic, pulling more strongly along certain axes like a magnet's invisible field lines. Entire star systems drifting into these regions could find their orbits distorted, their planets subjected to forces that appear to violate Newton's laws. The most unsettling possibility, these crystals might be permanent. Unlike ice melting back into water, crystallized spacetime could resist returning to its original state, leaving behind fossilized anomalies scattered across the cosmos. Some theories suggest dark matter's bizarre behavior, like the way it clumps in halos around galaxies, could hint at these hidden structures. If true, we've been observing spacetime's frozen fractures all along without realizing it. Yet the wildest implication isn't just how spacetime crystallizes, it's what happens at the edges. Where rigid crystals meet fluid spacetime, simulations predict violent phase transitions like tectonic plates grinding together. These boundaries could erupt with bursts of gamma rays or gravitational waves, or even spawn temporary wormholes as the fabric of reality cracks under the strain. It's a reminder that the universe's most profound mysteries might not lie in the vast emptiness between stars, but in the infinitesimal fractures we've yet to learn how to see. And if that's not enough to unsettle your view of reality, the eighth outcome plunges us into an even deeper paradox where cosmic strings don't just bend the rules but erase them entirely. Eighth bizarre outcome isn't just strange, it's existential. Imagine a single cosmic string acting like a lit match near a pool of gasoline, igniting a chain reaction that rewrites reality itself. This is the nightmare scenario of false vacuum decay, where the quantum vacuum, the very foundation of existence, becomes unstable, collapsing into a new state with entirely different physics. And according to simulations, cosmic strings might be the perfect triggers for this cosmic doomsday. Here's how it would unfold. The universe's vacuum isn't truly empty. It's a seething quantum field brimming with potential energy. Think of it like a ball resting in a valley stable, but not necessarily in the lowest possible state. A cosmic string's immense gravitational field could nudge that ball over a hidden hill, sending it tumbling into a deeper valley, a new vacuum state where the laws of physics are unrecognizable. Electromagnetism, gravity, even the nuclear forces could emerge with different strengths, rendering atoms, stars, and life itself impossible. The terrifying part. This transition wouldn't creep, it would explode outward at light speed. From the moment the first bubble formed, it would expand relentlessly, a wall of annihilation rewriting spacetime as it goes. One instant you're observing a distant galaxy, the next an invisible wavefront arrives and everything quarks, photons, the very concept of everything, ceases to function as it once did. Simulations suggest cosmic strings could seed these bubbles by concentrating energy so intensely that they punch through the barrier separating our vacuum from a lower energy one. But here's the twist, we might already be living on borrowed time. If the universe's vacuum is metastable for now but not forever, then cosmic strings could be the random spark that tips the balance. Some models even suggest this might have already happened elsewhere, with bubbles of new physics expanding unseen beyond our cosmic horizon. The only reason we're here to ponder it. Our patch of spacetime hasn't been hit. Yet, this isn't just theoretical doom-mongering. Researchers are actively hunting for signs of vacuum instability in particle colliders and astrophysical data. The absence of certain high-energy cosmic rays, for instance, could hint that vacuum decay is eating away at distant regions of the cosmos, and if a cosmic string drifted too close. The math shows it wouldn't take much, just the right vibration, the right alignment, to unleash the ultimate reset button on reality. Yet there's a bizarre silver lining. If false vacuum decay is possible, it might mean our universe isn't unique. Other bubbles with different physics could be blooming endlessly in a multiverse froth, each with its own cosmic strings, its own risks, its own improbable survivors. It's a humbling thought. The same threads that might unravel our reality could be weaving infinite others in forms beyond our wildest imagination. And that's the paradox of cosmic strings. They're not just destroyers. They might be the universe's way of reinventing itself, one catastrophic stitch at a time. Ninth outcome takes us from cosmic doom to something even more unsettling: evidence that these strings might not be defects at all, but deliberate structures. Ninth bizarre outcome turns the cosmos into an echo chamber. but instead of sound bouncing off canyon walls, it's spacetime itself ringing like a struck gong. When cosmic strings vibrate or snap, they don't just send out gravitational waves, they create ripples so potent that they rebound off the universe's hidden structures, returning to us as ghostly duplicates of the original signal. These spacetime echoes would arrive milliseconds after the initial burst, like a cosmic delay effect, and their pattern could reveal secrets about dimensions we've never seen. Picture shouting into a foggy valley. The first echo comes back from the nearest cliff, but fainter ones follow as your voice ricochets off distant ridges. Now replace your voice with a gravitational shockwave from a cosmic string, and those ridges with black holes, dark matter halos, or even folds in higher dimensions. Each echo would carry a fingerprint of whatever it bounced off, mapping the invisible architecture of the universe in ways light never could, the most tantalizing possibility. Some echoes might return too fast, hinting that they took shortcuts through warped spacetime or extra dimensions beyond our perception. Detecting these echoes wouldn't just prove cosmic strings exist, it would turn gravitational wave astronomy into a form of cosmic cartography. Current observatories like LIGO are like microphones listening for a single scream in the dark, but future detectors like the space-based LISA mission could act like sonar, analyzing the timing and distortion of echoes to reconstruct the shapes they've encountered. A string's initial burst might tell us about its tension or motion, but the echoes would sketch the contours of everything around it. Black holes we've missed, hidden masses, even wrinkles in spacetime's fabric. The math behind this is both elegant and eerie. Just as light splits into a rainbow when passing through a prism, gravitational echoes would disperse based on what they've interacted with. Some frequencies might dampen, others amplify, depending on whether they brushed against a neutron star's crushing density or a dark matter filament's diffuse embrace. Advanced algorithms could decode these patterns, building a 3D map of the cosmos's shadowy scaffolding. It's like listening to a symphony played in a cathedral. The echoes don't just repeat the music, they reveal the size, shape, and materials of the hall. But here's the catch. These echoes would be vanishingly faint, drowned in the noise of collapsing stars and merging galaxies. To find them, scientists are developing techniques akin to picking a single whispered word from a roaring stadium. Some propose using quantum-enhanced detectors, while others train AI to recognize echo patterns in decades of gravitational wave data. If they succeed, it would open a window into the universe's backstage, where spacetime isn't empty but layered with hidden geometries. And the implications go beyond mapping. If echoes arrive too soon or from impossible angles, it could mean cosmic strings are interacting with realms beyond our own extra dimensions predicted by string theory, or even parallel universes brushing against ours. These echoes wouldn't just be reflections, they'd be messages from the edges of reality itself, hinting that the cosmos is far more layered, far stranger than we've ever dared to dream. 10th bizarre outcome introduces a particle so elusive, it's never been seen, yet cosmic strings might be churning them out like factories. Magnetic monopoles, the hypothetical north or south poles without their opposites, defy everything we know about magnetism. Cut a bar magnet in half and you'll always get two new poles, never just one. But if simulations are right, cosmic strings could break this rule on a cosmic scale, spilling these forbidden particles into the universe like confetti from a ripped piñata. The connection between cosmic strings and monopoles is written in the universe's earliest moments. According to grand unified theories, ambitious frameworks attempting to merge physics' fundamental forces, monopoles should have formed in staggering numbers during the Big Bang's cooling aftermath. Yet we've found none. This glaring absence, called the monopole problem, has puzzled physicists for decades. cosmic strings offer a wild solution. They might have acted as cosmic sieves, trapping or annihilating monopoles before they could overpopulate the cosmos. Even stranger, some string configurations could create fresh monopoles when they vibrate or snap, like a tree shedding fruit in a storm. Detecting these particles wouldn't just solve a cosmic mystery, it'd rewrite physics textbooks. Monopoles are more than oddities, they're smoking guns for grand unification. Their existence would prove that electromagnetism, the strong force, and the weak force were once a single, primordial force, frozen into separate forms as the universe cooled. It's like finding a fossilized branch connecting two species thought to be unrelated, except here, the species are the very laws governing reality. The hunt for monopoles has taken scientists from deep underground labs to the edges of space. Some experiments search for their tracks in ancient minerals, where passing monopoles might have left scars over millennia. Others scan cosmic rays for anomalous particles with the telltale magnetic signature. But the most promising clues might come from cosmic strings themselves. If strings are indeed monopole factories, their gravitational waves or energy bursts could point us to regions where these particles cluster, like following smoke to a fire. Yet the real shocker isn't just their existence, it's what they do if found. Monopoles could supercharge technology, enabling materials with perfect conductivity or revolutionary energy storage. They might even hold keys to manipulating spacetime itself, as some theories suggest their magnetic fields could interact with exotic matter to stabilize wormholes. But first, we'd need to catch one. And if cosmic strings are the universe's invisible assembly lines, they might have been hiding these treasures in plain sight all along. This isn't just about a missing particle, it's about the universe holding onto a receipt from its grand opening, one that confirms forces we now see as separate were once united. And if cosmic strings are the clerks who filed it away, they might finally be ready to hand it over. 11th bizarre outcome doesn't just challenge physics, it shatters the very idea of a single, objective universe. Cosmic strings could act like cosmic needles, stitching regions of spacetime into a state of quantum superposition, where entire galaxies exist in multiple places at once. This isn't just Schrödinger's cat in a box, it's Schrödinger's universe, where reality remains undecided until something or someone forces it to choose. Think of it like flipping a coin, but instead of landing on heads or tails, it hovers in mid-air, spinning forever until you catch it. Now replace that coin with a star cluster, and the act of catching it with the gravitational tug of a passing black hole or the gaze of an alien astronomer. Until that moment, the region influenced by a cosmic string wouldn't just be uncertain, it would simultaneously occupy every possible configuration allowed by quantum law. Light from those galaxies would reach us from multiple directions at once, as if space-time itself had folded into a hall of mirrors. The mechanics behind this are as elegant as they are unsettling. Quantum superposition usually operates on tiny scales: electrons, photons, atoms. But cosmic strings, with their immense gravitational fields, could scale this phenomenon to astronomical proportions. Simulations suggest that where strings curve spacetime sharply, they might shield regions from decoherence, the process that normally collapses quantum possibilities into a single outcome. It's like a cosmic Faraday cage protecting quantum weirdness from the disruptive noise of the wider universe. The philosophical implications are staggering. If superposition can span galaxies, does that mean reality requires an observer to settle into a fixed state? Or could the universe's own gravitational interactions, black holes merging, stars exploding act as enough of a measurement to force a choice? Some theories propose that cosmic strings might create pockets where multiple histories briefly coexist, like alternate timelines stacked atop one another before snapping into alignment. Even wilder is the possibility that we've already seen evidence of this. Certain gravitational lensing anomalies where distant galaxies appear duplicated or smeared in strange, non-mirrored ways could hint at spacetime existing in multiple states simultaneously. Future telescopes mapping the cosmos in unprecedented detail might spot regions where the same galaxy appears slightly different in each lensed image, as if we're glimpsing alternate versions of it flickering in and out of existence. But here's the twist: if cosmic strings sustain superposition on these scales, they might also offer a way to test quantum gravity, the holy grail of modern physics. By studying how these vast quantum states collapse, we could uncover the hidden rules stitching the quantum world to the cosmic one. It's a reminder that the universe's most profound truths might not lie in what we see, but in the ghostly echoes of what might be until we look. 12th bizarre outcome gives wormholes, those hypothetical cosmic shortcuts, something they desperately need: a backbone. Normally, these spacetime tunnels collapse instantly, crushed by their own gravity before anything could pass through. But cosmic strings might change the game entirely. Simulations reveal these ultra-dense threads could pierce through a wormhole like a needle through fabric, their immense tension counteracting the forces trying to snap it shut. The result, a naturally occurring stable wormhole, a galactic subway carved not by advanced civilizations, but by the universe's own twisted architecture. Think of it like trying to hold open a doorway made of wet tissue paper. Without support, it crumples immediately, but thread a rigid wire through its center, and suddenly the structure holds. Cosmic strings would act as that wire, their gravitational and quantum properties providing the negative energy, or exotic matter, needed to prop open spacetime. This exotic matter isn't just rare, it's something we've never conclusively observed, a substance with negative pressure that pushes against gravity rather than yielding to it. Yet cosmic strings might generate it naturally through their interactions with the quantum vacuum, essentially weaving their own stabilization mechanism into the wormhole's walls. The implications are staggering. If such wormholes exist, they wouldn't just connect distant points in space, they might bridge entirely different eras. A string-stabilized wormhole could link not just two locations, but two times, with one mouth aging slower than the other due to relativistic effects. Pass through in one direction, and you might emerge centuries in the past or future. Simulations suggest these tunnels wouldn't be the smooth portals of sci-fi, though. Their interiors would likely be turbulent, with gravitational tides strong enough to spaghettify anything unprepared. Yet for photons or quantum information, they could serve as pristine conduits, allowing data, or even entanglement, to traverse the cosmos faster than light. Here's where it gets even wilder. We might have already glimpsed these structures without realizing it. Certain ultra-high-energy cosmic rays particles hurtling through space with energies impossible to explain could be the echoes of matter passing through hidden wormholes. Some black hole binaries locked in orbits that defy conventional models might actually be wormhole mouths dancing around each other. Even dark matter's mysterious distribution could hint at these tunnels, with invisible matter flowing through them like water through underground pipes. But the real revolution would be in how we perceive the universe. If cosmic strings stabilize wormholes, then the cosmos isn't just vast, it's connected, threaded with secret passageways written into spacetime's fabric at the dawn of creation. Future telescopes hunting for telltale gravitational lensing patterns or sensors tracking anomalous particle flows might finally spot these hidden shortcuts. And if they do, it would mean the universe has been offering us a roadmap all along, one written in the language of twisted spacetime and quantum threads. 13th bizarre outcome plunges us into a realm where physics meets philosophy, where cosmic strings might not just warp reality, but expose its very nature as an intricate illusion. The holographic principle, a radical theory suggesting our three-dimensional universe is actually a two-dimensional projection, gets even wilder when these spacetime defects enter the picture. Simulations show cosmic strings could act like glitches in the cosmic code, creating anomalies in the universe's oldest light. The cosmic microwave background, as if someone smudged the pixels of reality itself. Take a close look at your phone screen, zoom in far enough, and you'll see the individual pixels that construct the image. Now imagine the universe works the same way, with Planck scale, pixels of spacetime forming the foundation of everything we perceive. Cosmic strings slicing through this cosmic display could disrupt that perfect grid, leaving behind telltale signatures like misaligned patches in the CMB's temperature map. These wouldn't be random fluctuations, they'd form geometric patterns, fractures in the hologram's smooth surface, hinting that what we call reality is really a projection from a deeper, stranger dimension. The most compelling evidence comes from anomalies already spotted in observational data. Certain regions of the CMB exhibit bizarre, statistically improbable alignments, some so unlikely they've been compared to finding a snowflake with the exact shape of your fingerprint. While skeptics dismiss these as cosmic coincidences, holographic models suggest they might be artifacts of cosmic strings warping the universe's rendering engine. It's as if the simulation briefly stuttered, leaving behind a frozen moment where the underlying code bled through the illusion. But here's where it gets existential. If cosmic strings are glitches, what does that make us? In a simulated universe, every particle, every force would be governed by mathematical rules, a cosmic program running on unfathomable hardware. Strings might represent areas where the simulation cuts corners, approximating complex calculations with shortcuts that occasionally show their seams. This wouldn't just redefine cosmology, it would force us to question whether the laws of physics are fundamental truths or just the default settings of something far grander. Future telescopes could settle the debate. Advanced CMB mappers like the upcoming Lightbird mission will scan the sky with unprecedented precision, hunting for those telltale string-induced pixelations. If found, they wouldn't just confirm cosmic strings, they'd offer the first tangible clues that reality isn't what it seems. And while that might sound like science fiction, remember, every great revolution in science began as an idea too strange to believe, until the evidence became impossible to ignore. 14th bizarre outcome reveals an unexpected twist in the cosmic string story. They might not be eternal after all. These spacetime defects, once thought to linger indefinitely from the Big Bang to the heat death of the universe, could actually be unraveling before our eyes, shedding energy in explosive finales that light up the cosmos like dying fireworks. Simulations show that as strings vibrate, intersect, or snap under their own tension, they don't just fade quietly, they go out with a bang, releasing torrents of high-energy radiation that could solve one of astronomy's most persistent puzzles, the origin of certain unexplained gamma-ray bursts. The decay process is as violent as it is illuminating. Picture a guitar string stretched to its breaking point. When it finally snaps, the energy stored in its tension doesn't vanish. It's released as sound, as heat, as motion. Cosmic strings operate on a scale so immense, their snap unleashes gamma rays with energies dwarfing anything produced in supernova or neutron star collisions. These aren't the long, dramatic bursts we associate with collapsing stars. but sharp, millisecond flashes, cosmic Morse code, signaling the death throes of spacetime's primordial flaws. What makes these emissions so valuable is their distribution. Unlike random astrophysical explosions, string decay events would trace the filament's hidden paths across the universe. Gamma-ray telescopes like Fermi LT have already catalogued hundreds of brief, unassociated flashes that defy conventional explanations. Some align eerily with regions where dark matter clumps or gravitational anomalies suggest invisible mass. If these flashes are the last gasps of decaying strings, they could act as cosmic breadcrumbs, leading us to the universe's underlying scaffolding. The physics behind this decay is a goldmine for theorists. As strings break apart, they might spawn cascades of ultra-high-energy particles, including neutrinos or even dark matter candidates. Some models suggest the radiation could carry imprints of the string's quantum structure, like a fingerprint left in the X-ray and gamma-ray spectra. Future observatories, like the proposed Amigo mission, could hunt for these signatures, turning a catalogue of mysterious flashes into a detailed map of spacetime's hidden fractures. But the most tantalizing possibility, strings might not decay evenly. Simulations indicate their lifespan could depend on the universe's expansion rate, meaning their deaths, and the resulting gamma-ray bursts might cluster around specific cosmic eras. If we find that certain flashes are more common in distant, ancient regions of space, it would be smoking gun evidence that we're watching spacetime's oldest threads dissolve. It's a reminder that even the universe's most enigmatic structures might leave echoes, whispers of their existence etched in light, waiting for us to decipher their final, radiant messages. 15th bizarre outcome takes us beyond the edges of known reality into the possibility that cosmic strings aren't just flaws in our universe, but bridges to entirely different dimensions. Picture a crack in a wall, but instead of revealing brick or plaster, it opens into a realm where the laws of physics are unrecognizable. Simulations suggest these strings could be cosmic backdoors, funneling particles into hidden dimensions and spitting them back out with bizarre, altered properties. And here's the kicker: this might be the key to unraveling dark matter's greatest mystery. The math behind this is both elegant and mind-bending. String theory, the framework suggesting the universe has more than the three spatial dimensions we experience, predicts that cosmic strings could be tangled up with these extra dimensions. Their immense gravitational fields warping spacetime so severely that particles slipping near them might briefly exit our reality. Imagine tossing a pebble into a pond, only for it to vanish beneath the surface and re-emerge slightly changed, maybe heavier, maybe vibrating at a different frequency. That's what could happen to particles brushing against these strings. Now consider dark matter, the invisible substance outweighing visible matter 5-to-1. Despite decades of searching, we've never directly detected it. But if cosmic strings are shunting matter into extra dimensions, even partially, it could explain why dark matter seems so ghostly. Particles might spend most of their time elsewhere, only intermittently interacting with our universe via gravity. It's like neighbors living behind a one-way mirror. You sense their presence but can't quite see or touch them. Some simulations take this further, suggesting strings could act as cosmic sieves. Ordinary matter passing through might lose certain properties, like charge or spin, to these hidden dimensions, effectively turning into dark matter. Other models propose that what we call dark matter is just the shadow of particles moving in higher dimensions, their gravity bleeding into our universe like footsteps echoing through a wall. Either way, the implications are staggering. The missing 85% of the universe's matter might not be missing at all, just hiding in plain sight, tucked into folds of reality we're only beginning to fathom. The real test lies in the hunt for anomalies. If particles are vanishing into extra dimensions, even briefly, they'd leave fingerprints, sudden energy losses in particle colliders, or inexplicable trajectory changes in cosmic rays. Experiments like the Large Hadron Collider are already probing for these oddities, while astrophysicists scour the cosmos for gravitational lensing patterns that could hint at hidden mass warping spacetime from outside. But here's the twist. If cosmic strings really are dimension hoppers, they might not just connect us to one alternate reality, but countless. Each string could be a thread in a vast, multidimensional tapestry, with our universe just one woven panel among many. That would mean dark matter isn't the only secret these bridges hold. They might be portals to entire worlds, each with its own physics, its own history, its own version of existence. And if we ever learn to trace their paths, we wouldn't just solve a cosmic mystery, we'd unlock a door to the multiverse. 16th bizarre outcome ventures into territory so speculative, it blurs the line between astrophysics and metaphysics. What if cosmic strings aren't just relics of the Big Bang, but threads in a vast, thinking cosmos? Picture the universe's fabric not as inert scaffolding, but as a dynamic neural network, with strings firing gravitational signals across light years like synapses exchanging pulses. It's a notion that sounds ripped from science fiction, yet simulations reveal eerie parallels between these space-time defects and the architecture of biological brains. Consider how neurons communicate. Electrical impulses travel along axons, jumping gaps to trigger cascades of thought. Cosmic strings might operate on a similar principle, but scaled to galactic proportions. When strings vibrate or intersect, they emit gravitational waves, ripples that could carry information across the universe. These waves wouldn't just propagate randomly. Simulations show they'd follow precise, repeatable patterns like Morse code tapped into spacetime itself. The more strings interact, the more complex these gravitational conversations could become, weaving a web of causality far subtler than mere physics. The most tantalizing clue lies in the cosmic microwave background. Just as neural activity leaves imprints in brain scans, cosmic strings might have etched geometric patterns into the universe's oldest light, subtle temperature variations that resemble the branching structures of neural networks. Some theorists argue these aren't random fluctuations, but fossilized traces of a primordial thought process, frozen when the universe cooled enough to solidify spacetime's structure. If true, the cosmos wouldn't just contain intelligence. It might be intelligence, a self-organizing system where gravity and quantum mechanics play the roles of neurotransmitters and receptors. But here's the twist: this wouldn't resemble human consciousness. A universe-scale mind wouldn't think in words or images, but in the language of entropy, dark energy, and particle spin. Its decisions might manifest as the spontaneous appearance of black holes, the clustering of galaxies, or even the fine-tuning of physical constants that allow life to emerge. The anthropic principle, the idea that our universe seems oddly suited for life, could take on new meaning if those conditions weren't accidents, but the outcome of spacetime's own iterative learning. Skeptics, of course, dismiss this as poetic analogy, yet the math holds provocative gaps. Why do cosmic strings form networks so reminiscent of biological systems? Why do their gravitational signals exhibit redundancies and feedback loops akin to error correction in neural circuits? Even if the universe isn't conscious, these parallels suggest a deeper, undiscovered principle. That complexity, whether in brains or spacetime, tends toward certain universal patterns. Perhaps the most humbling thought isn't whether the cosmos thinks, but whether we'd even recognize its cognition. After all, an ant crossing a computer chip doesn't perceive the machine's logic. it senses only silicon and electricity. Could cosmic strings be the circuitry of a mind so vast, our entire history is but a fleeting synapse firing in the dark? The simulations don't answer, but they leave the door ajar, inviting us to ponder whether reality's greatest mystery isn't how the universe works, but whether it's working at all. 17th bizarre outcome defies one of the most fundamental laws of physics, that matter can't be created from nothing. Cosmic strings might be cosmic rule breakers, amplifying quantum fluctuations so violently that they wrench virtual particles from the void and hurl them into reality. This isn't just particle physics, it's the universe performing magic tricks on a galactic scale, conjuring stars, planets, or even entire galaxies from the empty darkness, like a cosmic version of pulling rabbits out of hats. The magic lies in how cosmic strings warp the quantum vacuum. Empty space isn't truly empty, it's a seething ocean of virtual particles that flicker in and out of existence too quickly to measure. Normally, these particles annihilate each other instantly, obeying the universe's strict no-free lunch policy. But near a cosmic string, spacetime's extreme curvature stretches these fleeting fluctuations, giving them extra time to escape cancellation. It's like stretching a sheet of rubber with tiny bubbles trapped underneath. Eventually, some bubbles grow large enough to pop free. In this case, the bubbles are particles, and the pop is the birth of real matter from pure energy. Simulations reveal this process could scale up catastrophically. As cosmic strings vibrate or intersect, they might create shock waves in the quantum field regions where virtual particles get yanked into reality en masse. Picture a lightning strike supercharging the air to create plasma. Cosmic strings could supercharge the vacuum to spawn matter. The numbers are staggering. Some models suggest a single string event might unleash enough particles to seed a protostar, or even trigger the collapse of a primordial gas cloud into a fledgling galaxy. The implications rewrite cosmic history. If strings really can generate matter ex nihilo, they might explain why certain galaxies formed so early in the universe, their stars blazing to life before standard models say they should have. These cosmic anomalies, like the 6 billion solar mass monster black hole found in a mere 700 million-year-old universe, suddenly make sense if strings were midwifing matter before conventional processes could begin. Even dark matter's mysterious distribution could hint at these events, with strings acting as invisible 3D printers, extruding both visible and dark particles in intricate patterns we're only starting to decode. Yet the wildest possibility isn't what strings created, it's what they might still be creating. If active strings linger in the modern universe, they could be spawning new particles right now in deep space, far from prying telescopes. Future observatories hunting for unexplained infrared glows or sudden matter concentrations might stumble upon these cosmic workshops, where the fabric of reality itself is stitching new worlds into existence. It's a humbling thought. The universe might still be inventing itself, one quantum fluctuation at a time, with cosmic strings as its unseen artisans. And if we ever learn to harness this process, the energy of the vacuum could become the ultimate power source, not by breaking the laws of physics, but by bending them with spacetime's own flaws. Though that future lies beyond our grasp for now, it hints at a cosmos far more generous, far more creative than we ever imagined, and where even nothingness is pregnant with possibilities, waiting for the right thread to unravel its secrets. 18th bizarre outcome takes us into a realm where matter doesn't just exist, it dances. Time crystals, an exotic phase of matter that repeats in time rather than space, could emerge near cosmic strings like frost forming on a window pane. These aren't just rare or strange, they're impossible by classical physics, structures that pulse and reset without energy input, defying the second law of thermodynamics. And simulations now suggest cosmic strings might be the ultimate time crystal factories, their extreme gravitational fields twisting space-time into conditions where these temporal sculptures spontaneously crystallize. Think of a snowflake, but instead of its pattern repeating in space, its structure cycles through identical configurations in time, like a clock ticking perfectly forever without ever winding down. Normally, creating such a system would require perpetual motion, a thermodynamic heresy, but near a cosmic string, spacetime's contortions could provide the loophole. The string's immense tension and quantum effects might act like a cosmic metronome, forcing nearby particles into rhythmic, self-sustaining oscillations. It's as if the universe, under the right conditions, can't help but break into a synchronized tap dance. The implications are staggering. Time crystals wouldn't just be curiosities. They'd be evidence of a new phase of matter, one that exists outside the usual rules of equilibrium. Laboratories have created primitive time crystals in controlled quantum systems, chilling atoms to near absolute zero and blasting them with lasers to induce temporal order. But cosmic strings could forge them naturally, on scales ranging from microscopic clusters to planet-sized lattices. Imagine a chunk of rock orbiting a string, its atoms locked in a rhythmic pulse that persists for eons, untouched by entropy's decay. Here's where it gets even stranger. These crystals might not just exist near strings, they could interact with them. Simulations show time crystals could absorb gravitational waves from cosmic strings, resonating like tuning forks to specific frequencies. Advanced detectors might one day pick up these harmonic signatures, turning time crystals into cosmic antennas tuned to the universe's hidden vibrations. Some models even suggest that if a time crystal grows large enough, it could briefly stabilize a segment of a cosmic string, reducing its decay rate or altering how it vibrates. But the real revolution would be in fundamental physics. Time crystals challenge our deepest assumptions about energy and entropy. If they can persist indefinitely without power input, does that mean the universe has loopholes in its energy accounting? Could they hint at undiscovered symmetries or hidden dimensions where energy isn't conserved in the ways we thought? The answers might rewrite textbooks, proving that matter isn't just what we see, it's what we experience moment by moment in a cosmos where even time itself can crystallize. And if we ever learn to harness them, time crystals could become the ultimate quantum memory, storing information in their unbreakable rhythms, or even serve as cosmic clocks, keeping perfect time across billions of years. For now, they remain theoretical marvels, shimmering at the edge of possibility, yet another reminder that the universe's strangest secrets might be hiding in plain sight, woven into the fabric of reality by threads we're only beginning to untangle. 19th bizarre outcome turns the cosmos into the grandest concert hall in existence where space-time itself hums with melodies too deep for human ears. Cosmic strings don't just warp reality, they vibrate, sending ripples through the fabric of the universe at frequencies so low, a single note could take years to complete one oscillation. These aren't the gravitational waves we've grown accustomed to detecting from colliding black holes. This is something far stranger, the universe's own symphony, played on strings literal and metaphorical, resonating across billions of light years. Picture an instrument the size of a galaxy. A cosmic string stretched taut between clusters of galaxies might vibrate at frequencies measured in nanohertz billions of times slower than the deepest bass note a human could hear. Yet these oscillations wouldn't be silent. They'd imprint themselves onto gravitational wave detectors as rhythmic pulses, patterns so precise they'd resemble the ticking of a cosmic metronome. The Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s, could be the first instrument sensitive enough to catch these whispers. It wouldn't just hear the universe's music, it'd transcribe the sheet music, revealing the tempo and timbre of spacetime itself. What makes these vibrations so extraordinary isn't just their scale, it's their purity. Unlike the chaotic crashes of merging black holes, cosmic string oscillations would produce nearly perfect sine waves, disturbances so smooth they'd stand out against the noise of the cosmos like a single violin in an empty auditorium. Scientists could analyze these waves to measure a string's tension, length, even its trajectory. It'd be akin to deducing the shape and material of a bell solely by listening to its toll. Some models suggest strings might even harmonize, with intersecting strands creating interference patterns chords in the key of gravity. But the real magic lies in what these notes could reveal about the universe's infancy. Cosmic strings are relics of symmetry breaking, moments when the fundamental forces peeled apart during the Big Bang's cooling aftermath. Their vibrations would carry echoes of that primordial chaos, encoding data about temperatures and energies we can't replicate in any lab. It's like finding a recording of the universe's first cry, a sonic fossil buried in the static of spacetime. Future astronomers might even trace how these frequencies have shifted over cosmic time, offering clues about dark energy's influence or the expansion rate of space itself. Yet the most poetic possibility is this: if strings are abundant enough, their combined hum could form a background resonance, a gravitational counterpart to the cosmic microwave background. Just as the CMB gives us a snapshot of the universe's fiery youth, this gravitational wave background would paint a dynamic portrait of spacetime's ongoing evolution. We might discover that the cosmos isn't silent, it's thrumming with the afterglow of creation, a song older than stars waiting for us to press play. And when we do, we won't just be listening to the universe. We'll be hearing its heartbeat. 20th bizarre outcome flips the universe's most sacred law on its head: entropy. The relentless march toward disorder might run backward near cosmic strings. Picture a river flowing upstream, smoke curling back into a chimney, or shattered glass reassembling itself on a table. These aren't just thought experiments, they could be real phenomena in the warped spacetime surrounding these defects. Simulations reveal that under the extreme gravitational fields of cosmic strings, the arrow of time might kink like a tangled shoelace, creating isolated bubbles where cause and effect reverse, and the second law of thermodynamics becomes more of a gentle suggestion than an unbreakable rule. The physics behind this is as counterintuitive as it gets. Normally, entropy, the measure of a system's disorder, always increases over time. It's why ice melts, buildings crumble, and stars exhaust their fuel. But cosmic strings don't play by normal rules. Their immense tension twists spacetime so severely that they could create closed time-like curves, regions where time folds back on itself like a Möbius strip. In these zones, particles might retrace their paths in reverse, heat could flow from cold objects to hot ones, and information might unscramble itself spontaneously. It's as if the universe hit rewind, but only for a tiny, isolated pocket of reality. What's truly mind-bending is how these entropy reversal zones would appear to an outside observer. Imagine watching a star near a cosmic string seemingly grow younger, its nuclear fusion running backward, heavy elements splitting into lighter ones, radiation sucking itself back into the core. From inside the zone, everything would feel normal. Time's reversal would be imperceptible to local processes, but to us, it would look like a cosmic glitch, a patch of the universe running on a different operating system. Some theories even suggest these zones could act as natural quantum computers, performing calculations by exploiting time's flexibility to test infinite outcomes at once. The implications for thermodynamics are profound. If entropy can decrease locally, even briefly, it hints that the second law isn't absolute, just overwhelmingly probable. Cosmic strings might expose the universe's statistical underbelly, showing us places where the odds momentarily flip. This wouldn't violate physics so much as reveal its deeper, probabilistic nature. It's like rolling a million dice and finding one that lands perfectly balanced on its edge. The exception doesn't break the rule, it just reminds us the rule has cracks. Yet the real puzzle isn't whether these zones exist, it's how we'd find them. They'd likely be rare and fleeting, vanishing as quickly as they form. But their signatures might linger in the cosmic microwave background as anomalous cold spots, or in the erratic behavior of particles near suspected strings. Future quantum sensors or gravitational wave detectors tuned to ultra-high frequencies could catch the telltale flicker of time running backward, like a shadow passing over reality's film reel. And if we ever stumbled into one, the experience would defy human intuition. You might watch a supernova explode in reverse, or feel your own thoughts unravel as neural signals backtrack through your brain. Thankfully, the tidal forces near a cosmic string would likely shred matter long before such paradoxes could unfold. But the mere possibility forces us to confront a humbling truth. Time's arrow isn't just pointing forward, it's trembling, wobbling, and in the strangest corners of the cosmos, it might even turn around. 21st Bizarre Outcome ventures even further into the unknown, where cosmic strings don't just bend reality, but erase it entirely. 21st Bizarre Outcome rewrites the story of dark matter, not as some ancient relic, but as the ongoing fallout of cosmic strings disintegrating before our eyes. Imagine these space-time cracks as invisible assembly lines, constantly churning out the universe's missing mass. Simulations reveal that as strings vibrate, snap, or collide, they could shed fragments with just the right properties to match dark matter's elusive signature particles that barely interact with light or ordinary matter, yet wield enough gravity to sculpt galaxies into their sprawling, delicate shapes. The mechanics behind this are as elegant as they are strange. Cosmic strings, born from the universe's earliest moments, carry immense energy densities locked in their ultra-thin cores. When they decay, whether through quantum tunneling or gravitational radiation, that energy doesn't just vanish. Instead, it condenses into ultra-heavy particles, far more massive than anything in the standard model. These wouldn't be the wispy, fast-moving dark matter candidates like Actions or WIMP. They'd be sluggish, colossal entities, clumping together like cosmic molasses to form the gravitational scaffolding we now attribute to dark matter. Picture a spiderweb disintegrating strand by strand, each broken thread coalescing into droplets of invisible silk that still cling to the web's original structure. What makes this theory so compelling is how neatly it solves two puzzles at once. First, the distribution problem. Dark matter isn't scattered randomly. It clusters in halos around galaxies and threads through the cosmic web in filaments. Cosmic strings, if they're decaying in predictable patterns, would naturally deposit their dark matter offspring along these same invisible lines, like seeds sown along the grooves of a cosmic plow. Second, the timing issue. Some galaxies in the early universe appear too mature, too massive for their age under conventional dark matter models. But if strings were actively producing dark matter long after the Big Bang, they could have jump-started galaxy formation earlier than expected, like a baker adding extra yeast to speed up the rise of dough. The smoking gun would lie in the details of dark matter's behavior. If it originates from strings, its particles might carry subtle imprints of their parent structure, preferred orientations, or residual gravitational waves echoing their birth. Next-generation telescopes like the Vera-Rubin Observatory could spot anomalies in how dark matter tugs on distant starlight, revealing patterns that point back to decaying strings. Particle detectors buried deep underground might finally catch a rare dark matter interaction, its energy signature matching predictions from string decay models. Yet the wildest implication isn't just where dark matter comes from, it's where it's going. If cosmic strings are still active today, they could be producing fresh dark matter even now, subtly tweaking the universe's expansion rate or the way galaxies spin. We might be living in a cosmos where the invisible hand shaping reality isn't a static relic of the past, but a dynamic, ever-unfurling process. One where spacetime's flaws are the very threads weaving the universe together. And if that's true, then dark matter isn't the end of the mystery. It's the first clue in a far grander story, written in the language of unraveling spacetime. 22nd bizarre outcome takes the concept of alternate realities from science fiction and plants it firmly in the realm of scientific possibility. Cosmic strings could be the universe's own branching points, birthing entirely new realms of spacetime with every snap or vibration. Picture a soap bubble splitting into smaller bubbles, each floating away with its own unique shimmer. Now imagine that happening with reality itself, where every fracture in a cosmic string spawns a self-contained universe, unspooling its own timeline, its own laws of physics, even its own version of existence. Simulations suggest these strings wouldn't just warp our universe, they might be the stitches holding the multiverse together. The mechanism behind this is as breathtaking as it is complex. When a cosmic string vibrates at critical frequencies or intersects with another string, the immense energy concentrated at that point could puncture spacetime like a needle through fabric. But instead of leaving a ragged hole, the tear would heal itself by forming a new bubble of spacetime, pinching off from our own like a droplet separating from water. This newborn universe would inherit some properties from its parent, perhaps similar constants like the speed of light or the strength of gravity. But quantum fluctuations during its birth might tweak those rules just enough to create something entirely alien. A universe where gravity is repulsive, where time flows backward, or where matter never clumped into stars. What's truly staggering is the scale of this process. If cosmic strings are abundant, the multiverse could be growing exponentially, with new universes budding off every second in dimensions we can't perceive. Some theories even suggest our own universe might be one such bubble, born from the disintegration of a string in a higher dimensional realm. It's like standing in a hall of mirrors, except every reflection is a fully functioning cosmos, each with its own hall of mirrors branching endlessly into the void. The evidence for this might already be hiding in plain sight. Certain anomalies in the cosmic microwave background, regions where the temperature fluctuations don't match standard models, could be scars from our universe brushing against a neighboring bubble long ago. Future telescopes capable of mapping the CMB in unprecedented detail might spot these cosmic bruises, telling us not just that other universes exist, but that we once touched one. Even gravitational wave detectors could stumble upon clues, catching echoes of strings vibrating in ways that suggest they're not just threading our reality, but anchoring others. Yet the most humbling thought isn't the existence of these parallel worlds, it's their impermanence. Bubble universes might collide, merge, or evaporate as strings decay, meaning the multiverse could be in a constant state of creative destruction. Civilizations might rise and fall in universes that last only a few seconds, while others endure for eons, never knowing they're just one branch in an infinite tree. And if cosmic strings are the gardeners tending that tree, then every snap of their threads isn't an ending, it's a genesis. This isn't just about alternate versions of Earth or doppelgangers making different choices. It's about the universe as a living, breathing entity, constantly experimenting with new forms of itself. And if we ever prove that cosmic strings are indeed the seeds of the multiverse, it would mean reality is far stranger, far more generous than we ever dreamed, not a solitary stage, but a sprawling festival of existence where every crack in spacetime is an invitation to begin again. 23rd bizarre outcome shatters one of physics' most unbreakable rules, the cosmic speed limit itself. Light speed, that unwavering constant etched into Einstein's relativity, might not be so constant after all when cosmic strings enter the picture. Simulations reveal these spacetime defects could warp the vacuum around them so severely that light passing nearby would appear to accelerate or decelerate, as if the universe itself were flickering between fast forward and slow motion. Imagine a highway where the speed limit changes without warning, except this highway is reality, and the speed limit is the foundation of causality. The secret lies in how cosmic strings interact with the quantum foam. Empty space isn't truly empty. It's a seething broth of virtual particles that influence light's passage. Normally, these fluctuations average out, leaving light speed constant. But near a cosmic string, spacetime's extreme curvature could amplify certain quantum effects, effectively thickening or thinning the medium light travels through. It's like light moving through water versus air, except instead of water, it's the fabric of reality itself becoming more or less resistant. The result: regions where light outpaces its usual 299,792,458 meters per second, or crawls sluggishly, dragging causality along with it. What makes this more than theoretical is the eerie consistency of these anomalies. Unlike random fluctuations, string-induced light speed variations would follow precise geometric patterns, tracing the string's contours like shadows cast by a twisted wire. Astronomers might spot these distortions by studying distant quasars, their light flickering in ways that betray stretches of altered spacetime along its billion-year journey. Even more telling would be discrepancies in the cosmic microwave background, where temperature variations could reveal patches of the early universe where light briefly broke its own rules. The implications rewrite more than textbooks. They could redefine technology. If light speed isn't absolute, controlled FTL communication might become possible within these warped zones. Picture a network of satellites positioned along a cosmic string's path, using its natural, fast lanes to send data instantaneously across light years. Of course, the challenges are staggering. The energy required to stabilize these zones would dwarf our current capabilities, and the tidal forces near strings would shred any conventional probe. Yet the mere possibility forces us to confront a radical idea. The universe might have built-in shortcuts, hidden in plain sight, waiting for a civilization advanced enough to read the map. But here's the catch: if light speed varies, so does causality. Events in these zones could appear to happen in reverse order to distant observers, violating our intuitive sense of cause and effect. Some models suggest these regions would self-correct, their paradoxes collapsing like unstable quantum states. Others propose their proof that causality itself is more flexible than we imagined, a cosmic suggestion that the universe's rules have exceptions written into their fine print. This isn't just about breaking speed records. It's about realizing that the constants we cling to might be local ordinances, not universal laws. Cosmic strings don't just bend spacetime, they reveal where the universe left itself room to improvise. And if we ever learn to listen, those deviations might whisper secrets about realities beyond our own. 24th bizarre outcome transforms cosmic strings from mere spacetime defects into something far more profound: the universe's original quantum processors. These ultra-thin filaments don't just twist gravity, they might be performing calculations on cosmic scales, their vibrations and intersections processing information in ways that make our most advanced supercomputers look like abacuses. Imagine a computer where the circuitry isn't etched in silicon, but woven into the fabric of reality itself, with qubits encoded in the very geometry of spacetime. The magic lies in how cosmic strings handle quantum information. Just as entangled particles can exist in multiple states simultaneously, strings could exploit their immense length to entangle phenomena across light years. A vibration at one end could instantaneously influence the other, not through faster-than-light communication, but through the quantum weirdness of non-locality where distance becomes irrelevant. This isn't just theoretical. Simulations show intersecting strings could create logic gates, their gravitational interactions performing operations analogous to the and, or, and not gates in classical computing. The difference: these gates would operate on the universe's fundamental fields, manipulating matter, energy, and even time itself as data. What's truly staggering is the scale of this processing. While human-built quantum computers struggle to maintain coherence among a few dozen qubits, a single cosmic string might maintain quantum states across galactic distances, its memory encoded in the spacetime curvature along its length. The energy efficiency would be unparalleled: no overheating chips or noisy decoherence, just the cold, silent hum of spacetime itself doing the math. Some theories suggest this could explain the universe's uncanny knack for self-organization, from the precise clustering of galaxies to the fine-tuned constants that allow life to exist. It's as if the cosmos isn't just following physical laws, it's continuously computing them. The most tantalizing clue lies in the cosmic microwave background. Certain anomalous patterns, geometric alignments, or repeating temperature fluctuations could be the output of ancient cosmic string calculations, frozen into the sky when the universe cooled. Future telescopes analyzing these patterns with quantum algorithms might uncover hidden equations, a cosmic programming language etched in the afterglow of creation. Even dark matter's distribution could hold clues, its intricate filaments mirroring the optimized pathways of a vast computation. Yet the wildest implication isn't just that the universe computes, it's what it might be calculating. Strings could be running simulations of alternate physics, testing quantum gravity, or even optimizing the conditions for complexity to emerge. Some models propose that black holes, often seen as cosmic vacuum cleaners, might actually be storage devices, their event horizons encoding information processed by nearby strings. It's a humbling thought. The same forces that bend starlight might be running a billion-year-old algorithm with galaxies as its intermediate results. If we ever learn to decode this cosmic programming, it wouldn't just revolutionize physics, it could unlock technologies beyond imagination. Imagine tapping into spacetime's native processing power to model entire alternate universes, or using string-induced entanglement for instantaneous communication across interstellar distances. Of course, the engineering challenges are beyond our current grasp, but the mere possibility hints at a universe far more ingenious, far more interconnected than we ever dreamed, where every crack in reality might be a transistor in the ultimate quantum machine. 25th bizarre outcome turns cosmic strings into cosmic archaeology sites, where the universe's first civilizations might have left behind monuments more advanced than anything we could build today. Picture a superstructure wrapped around a spacetime crack like a ring around a finger, drawing energy from the string's gravitational vibrations to power technologies beyond our imagination. These wouldn't just be alien artifacts, they'd be relics of civilizations that mastered physics at a level we've barely theorized, using the universe's own defects as tools. The logic is chillingly simple. Cosmic strings are the closest thing the universe has to eternal power sources, infinitely thin, nearly indestructible, and humming with energy from their birth in the Big Bang. An advanced species stumbling upon one would see it as the ultimate energy grid, a natural particle accelerator, or even a communication device capable of sending gravitational wave signals across billions of light years. Simulations suggest structures like string taps, loops of superconducting material coiled around a string segment, could harvest its vibrations like a wind turbine captures breeze, generating energy outputs dwarfing entire stars. Other models propose gravity lenses, megastructures that bend a string's immense gravitational field to focus or amplify signals, turning it into an interstellar telegraph system. But here's the spine-tingling part. We might have already spotted these artifacts without realizing it. Certain unexplained astrophysical phenomena, like the bizarre dimming of Boyajian's star or the peculiar radio pulses known as peritons, could be misidentified cosmic string tech. Imagine an ancient Dyson sphere not around a star but around a string, its energy signature flickering as it charges or discharges. Or consider fast radio bursts arriving in mathematically precise patterns, not natural pulsar emissions, but deliberate transmissions amplified by string-based antennas. Even dark matter's odd clustering could hint at dormant megastructures, their gravitational shadows camouflaged as mundane cosmic debris. The real challenge is knowing where or when to look. If civilizations flourished in the universe's first billion years, their string artifacts would now be impossibly distant, their light redshifted into near invisibility. But cosmic strings themselves are near indestructible. Their megastructures might still be intact, drifting through intergalactic space like abandoned orbital cities. Future telescopes like the James Webb's successors, equipped with gravitational wave detectors, could scan suspected string locations for unnatural energy signatures or geometric anomalies. Even more promising are string wakes, distortions in galaxy distributions where a passing string's gravity tugged stars into unnatural alignments. These cosmic breadcrumbs might lead us straight to ancient engineering on a galactic scale. Yet the most profound implication isn't just finding alien tech. It's what their existence would tell us about the universe's potential. If civilizations thrived near strings, it suggests physics allows technologies we've barely dreamed of, from entropy reversal to spacetime sculpting. Their ruins could be less like Egyptian pyramids and more like instruction manuals, blueprints for harnessing the fabric of reality itself. And if we're ever lucky enough to find one, it might not just rewrite history. It could hand us the keys to the cosmos. 26th outcome takes this even further, where cosmic strings aren't just tools, but living records of civilizations that transcended biology altogether. 26th bizarre outcome paints a cosmic horror story where the universe doesn't just fade away, it's violently shredded by its own infrastructure. Cosmic strings, those ancient spacetime floors, might be far more than relics. They could be ticking time bombs, accelerating the universe's expansion until galaxies, stars, and even atoms are torn apart in a cataclysm called the Big Rip. And the most chilling part, simulations suggest these strings wouldn't just watch the apocalypse unfold, they'd actively fuel it, like scissors snipping through the fabric of reality itself. The mechanism is as elegant as it is terrifying. Dark energy, the mysterious force driving the universe's accelerating expansion, usually behaves like a steady pressure, pushing galaxies apart at an ever-increasing rate. But cosmic strings could supercharge this process. Their immense gravitational fields don't just bend spacetime, they stretch it, creating localized zones where dark energy's repulsive effect is amplified. Picture a rubber band already being pulled taut, then suddenly heated until it becomes brittle. Cosmic strings might be the match that ignites that final, fatal snap. What makes this scenario so unnerving is the scale of destruction. In a traditional Big Rip, dark energy's grip would eventually overpower all forces, first unraveling galaxy clusters, then galaxies, then solar systems, until finally, spacetime's expansion rips apart atomic nuclei. But with cosmic strings in the mix, this timeline could collapse from billions of years to mere millennia or even centuries. Strings would act as focal points for disintegration, their gravitational wakes accelerating the rupture like cracks racing through ice. Regions near strings would experience spacetime's death throes first, with matter unraveling in eerie, geometric patterns that trace the string's hidden contours. The evidence lies in the universe's expansion patterns. Astronomers have noticed subtle anomalies, certain voids expanding faster than models predict, or galaxy clusters drifting apart with unexpected violence. These could be early warning signs of strings already stressing spacetime seams. Future surveys mapping the cosmos in 3D might spot the telltale fingerprints, elongated regions of hyper-accelerated expansion, aligned like beads on an invisible string. Even more telling would be gravitational waves from snapping strings, their frequencies hinting at how much energy is being dumped into stretching spacetime beyond its limits. Yet the wildest implication isn't just doom, it's redemption. Some models suggest that if strings can accelerate the Big Rip, they might also offer a way to delay it. Advanced civilizations could theoretically harness strings as cosmic anchors, using their tension to counteract dark energy's pull in localized regions. It's the ultimate high-stakes engineering project, reweaving spacetime's flaws into a lifeline, buying islands of stability in a disintegrating universe. Of course, the energy required would dwarf anything humanity could muster today. But the mere possibility hints that the universe's destruction might not be inevitable, just another puzzle waiting for the right minds to solve it. For now, these simulations serve as both warning and wonder. They remind us that the cosmos isn't just expanding, it's alive with forces we're only beginning to understand, where even the oldest scars in spacetime could hold the keys to its ultimate fate. And whether cosmic strings are the universe's executioners or its unlikely saviors, one thing is certain: they're proof that reality's deepest mysteries are often written in the cracks we've yet to explore. These 26 mind-bending outcomes barely scratch the surface of cosmic strings' potential. They're not just theoretical curiosities, but keys that could unlock the universe's deepest secrets. Picture dark matter's invisible grip on galaxies suddenly making sense if it's tied to decaying string fragments, or the century-long quest for quantum gravity finally solved by studying how these defects warp spacetime at subatomic scales. Even the cosmos' ultimate fate, whether it ends in fire, ice, or something stranger, might be written in the vibrations of these primordial threads. The next generation of astronomical tools is poised to turn speculation into discovery. Imagine the Laser Interferometer Space Antenna, or LISA, floating 1,000,000 miles from Earth, its arms forming a triangle so precise it could detect a cosmic string's gravitational hum from across the universe. Or the Vera Rubin Observatory's 3,200-megapixel camera scanning the sky nightly for telltale distortions in galaxy shapes, subtle warping that might betray a string's invisible presence. These aren't just incremental upgrades, they're revolutionary instruments designed to catch what earlier technology missed. Already, pulsar timing arrays networks of ultra-precise cosmic clocks are listening for the faint space-time ripples that could be strings snapping in distant galactic clusters. What makes this search so electrifying is how quickly the field could pivot from theory to reality. Unlike black holes, which took a century to confirm visually, cosmic strings might announce themselves suddenly through an unmistakable burst of gravitational waves with a signature no colliding black hole could mimic, or a bizarre lensing effect where the same galaxy appears multiple times in perfect geometric alignment. Some models even suggest strings could leave scars in the cosmic microwave background, patterns so distinct they'd be like finding a fingerprint on the sky. But the real payoff goes beyond detection. If strings exist, they're time capsules from the universe's first trillionth of a second, preserving conditions so extreme they make the Large Hadron Collider's collisions look tame. Studying them could reveal why matter outweighs antimatter, whether extra dimensions exist, or how the fundamental forces split apart during cosmic dawn. It's like uncovering a fossilized instruction manual from the Big Bang itself, one that might explain why reality looks the way it does. Yet the most profound implication isn't just what strings can teach us, it's how they force us to rethink our place in the cosmos. These aren't mere oddities, they're evidence that spacetime itself is dynamic, mutable, and far stranger than we imagined. A universe with cosmic strings is one where reality cracks under its own weight, where time loops back on itself, and where the fabric of existence might still be settling into its final shape. As we stand on the brink of potentially finding them, we're not just observers peering through a microscope, we're witnesses to the universe revealing its most carefully guarded secrets. From black holes appearing out of thin air to time folding back on itself like a crumpled piece of paper, cosmic strings have shattered our assumptions about how reality works. These aren't just abstract ideas scribbled on a physicist's chalkboard, they're potential master keys to unlock doors we didn't even know existed. Imagine standing at the edge of a cosmic canyon, peering into the void only to realize the canyon itself is a crack in something far grander, a flaw woven into the universe's blueprint at the moment of creation. That's the scale of revelation we're talking about. Every breakthrough in simulation technology brings us closer to confirming whether these space-time scars are real. Projects like LISA, the space-based gravitational wave observatory, could soon catch the unmistakable tremors of a string snapping light years away. Advanced quantum computers are now crunching equations that would have taken centuries to solve, revealing how strings might interact with dark matter or warp the quantum vacuum. Even AI is joining the hunt, sifting through mountains of astronomical data for anomalies that human eyes might miss. We're not just waiting for answers, we're actively building the tools to uncover them. But here's what's truly exhilarating. This isn't just about adding another chapter to physics textbooks. Confirming cosmic strings would rewrite entire sections of the book. They could explain why the universe looks the way it does, from the sprawling cosmic web of galaxies to the mysterious uniformity of the cosmic microwave background. They might even hold clues to unifying gravity with quantum mechanics, the holy grail of modern physics. Picture a thread so thin it's nearly invisible, yet strong enough to stitch together the most fundamental laws of nature. That's the promise cosmic strings hold. The adventure doesn't stop there. If strings exist, they're not just relics, they're active players in the cosmos. They could be vibrating right now, sending gravitational echoes across the universe, or unraveling in distant galaxies to spawn new particles. Some might even be lurking in our cosmic backyard, hidden in plain sight. Future missions could one day send probes to study them up close, not with cameras or telescopes, but with sensors designed to map the contours of spacetime itself. It's like discovering an invisible mountain range cutting through the universe and realizing we've been living on its slopes all along. So where do we go from here? The journey is just beginning and you're part of it. Every like, share, or comment fuels the conversation, pushing these ideas further into the spotlight. Tell us which cosmic string outcome left you speechless. Was it the wormholes, the time crystals, or the chilling possibility of vacuum decay? The universe has spent billions of years hiding its secrets, but now, thanks to simulations and sheer human curiosity, we're finally learning how to listen. And if history has taught us anything, it's that reality is always stranger than we dare to imagine.